对。
Good afternoon, professors and classmates. Today, the special topic I want to share is creep and dynamic mechanical behavior of nature fiber functionalized carbon nanotubes modified epoxy composites by advisors Dr. Lee. The outline of this topic are introduction, experiment, results, and conclusion. The first part is introduction. Nature fibers such as flax, hemp, sisal, rayon, jute have gained great attention as reinforcement composites because they are low cost, low density, high specific strength and modulus, and they are also recyclable and biodegradable compared to the traditional glass and carbon fibers. Rayon fibers are extracted from stem bags and have an exceptional stress compared to other nature fibers. Physical properties of rayon fibers have been investigated, and the research results have shown that rayon fibers exhibit good thermal stability and high specific tensile properties. Thus, rayon fibers are considered as good reinforcing element in making polymer matrix composites. Creep is one of the principal properties of nature fibers reinforced polymer composites. Creep is the tendency of a solid material to move slowly or deform permanently under the influence of the mechanical stresses. It can occur as a result of long-term exposure to high levels of stress that are still below the yield strength of the material. The creep rate of deformation is a function of the material properties, exposure time, exposure temperature, and the applied structure law. Depending on the magnitude of the applied stress and its duration, the deformation can become so large that the component can no longer perform its function. The carbon nanotubes possess excellent mechanical, electrical, and thermal properties, making them an ideal candidate as reinforcing filler. Small dimensions of carbon nanotubes mean they have much greater interactions with composite matrix. However, an interfacial interactions between the polymer matrix and the carbon nanotubes is weak due to the inner nature of the carbon nanotubes. In order to improve the interactions between the epoxy resin and the carbon nanotube, various functionalized carbon nanotubes such as amino-functionalized, fluorinated, carboxylic acid functionalized were dispersed in the epoxy matrix to form composites. Upon curing, functionalized multiple carbon nanotubes with carboxylic acid groups are connected with the epoxy matrix by cross-linking reaction, and the interface between nanotube and epoxy can be improved. Traditional fiber reinforced carbon nanotubes modified matrix composites have attracted great attention in recent years. Relevant studies have shown that the fiber-dominated properties are not significantly affected by the introduction of carbon nanotubes, while matrix-dominated properties are improved to some extent. However, very limited work has been reported on the carbon nanotubes modified nature fiber reinforced polymer composites. In this report, the creep and dynamic mechanical behavior of rayon fiber and epoxy composites with or without carbon nanotubes were investigated. The effects of carbon nanotubes on the creep and dynamic mechanical behavior of composites were reviewed. The next part is experiment. There are 5 materials in this experiment. The first is functionalized multi-wall carbon nanotubes with 2.56 weight % carboxylic acid groups, and the outer diameter and length are 8 to 50 nanometers and approximately 50 micrometers respectively. The second is commercial woven rayon fabrics. The epoxy resin, curing agent, and accelerator used for composite preparation were FN-A62, micronized diisodiamide, and phenol. The accelerator was used for this purpose to reduce the curing temperature due to the limited thermal stability of nature fiber during composite processing. The next step is composite preparation. The multi-wall carbon nanotubes were first dispersed in the appropriate amount of acetone by mechanical stirring for 30 minutes followed by ultrasonication of that silicator for 4 hours. The epoxy resin, diglysosol ether of bisphenol F, was subsequently added to the multi-wall carbon nanotube suspension, followed by 30 minutes mechanical stirring to ensure good dispersion. And then the blend suspension was sonicated in a ultrasonic bed for 1 hour. The epoxy composite with 0.48% functionalized multi-wall carbon nanotubes remains at 60 degrees with the curing agent in the ratio of 1:8 and 1:2 by weight respectively. The remaining fabrics were dried in an oven at 120 degrees for 4 hours to remove moisture. The prepreg was produced by hand, and the residual acetone was removed at 80 degrees for 4 hours, and then at room temperature overnight. The composite was manufactured by hot press at 115 degrees under a pressure of 2.5 MPa, and then post-cure at 130 degrees for 2 hours. Natural fiber, epoxy two-phase composite were also processed by the same method. After the composite processing, are pre-test and dynamic mechanical analysis. Rectangular specimens with a size of 56 millimeters times 12 millimeters times 2.5 millimeters were made for the pre-test. Dynamic mechanical analysis instrument was used to measure deformation as a function of time. The tests were carried out in pre-mold using the 3-point bending fixture. 2 hours pre-test at 35 degrees with a constant stress level of 2 MPa were performed. The fracture surface of two-phase and three-phase composite under flight door loading were comparatively examined and analyzed by SEM. The SEM equipment and sample dimensions reported in pre-test were also used in dynamic mechanical analysis. Temperature scan from 55 degrees to 180 degrees with a frequency of 1 Hz were performed. The heating rate was 3 degrees per minute. Storage modulus and mechanical loss factor were measured as the function of temperature during the test. The next part is results. 2 hours free properties of two-phase and three-phase composite at 35 degrees were evaluated. This figure shows the effects of carbon nanotubes on the free properties of composite. It is observed that the creep deformation of three-phase composites decreased compared to two-phase composites, which shows the creep resistance of three-phase composites is better than two-phase composites. SEM observation also showed that the carbon nanotubes exist at the interface between ribbon fiber and epoxy resin, as the black ellipses in picture B compared to picture A. The temperature dependence of storage modulus for the two-phase and three-phase composite was shown in this figure. And the results show that the storage modulus of three-phase composite is higher than two-phase composites. This figure shows the glass transition temperature of two-phase and three-phase composite. It is noticed that the glass transition temperature of two-phase composite is 94.9 degrees, whereas the glass transition temperature of three-phase composite is increased by approximately 14 degrees. Both the increased storage modulus and glass transition temperature indicate the restricted mobility of resin molecules in the presence of the carbon nanotubes. The last part is conclusion. This report is about the effects of carbon nanotubes on the free and dynamic mechanical behavior of natural fiber and epoxy composites. The creep resistance and storage modulus of the composite with carbon nanotubes is higher than the composite without carbon nanotubes. The increased storage modulus and glass transition temperature of three-phase composite measured by dynamic mechanical analysis also showed consistent results with the pre-test. This is my special topic sharing. Thank you.
好，谢谢吴志勇同学来为我们做的这个报告哈。我们请老师跟同学们开始提问。
哎，他有。
不然说明一下，这边主要是在探讨什么？
探讨天然纤维跟环氧树脂的复合材料，它有加和没有加纳米碳管，它的一个动态力学性能以及它前面的一个现象。这样解释可以吗？
有没有听懂？好，这是复合材料，我补充一下，因为复合材料嘛，它这里告诉我们，这复合材料有加纳米碳管，这是强化材。你学复合材，像学陈国璋陈老师的这个复合材料的时候，就是呢，你的胶，还有呢你的木材，看一看呢，这个只要你加碳纤维，只要再加一个碳纤维材料的话，因为纤维强度5米还要高嘛，所以呢，它的一个力学强度就会强。所以呢，这里探讨了 creep 还有呢 dynamic 它的一个这个力学的一个性质，加了纳米碳管以后的是强化材，跟没有加，它差别在哪里？对不对？那有没有听懂？
所以纳米碳管加
纳米碳管是强化材加原来的这个，它有 two phase 跟 three phase，three phase 的话就是再加这个呢纳米碳管。那回答